All right. Okay. So today in the syllabus, this is not your class. Today in some other syllabus for some other class that isn't your class, there were different things. So let's see. In this one, we have where today is the 7th, and today is just a review. So it's all up to you guys what you want to hear, what you want to know. And then next class, it will be the midterm. Yes, Reagan.
So, can you give us an example where we would use the overhead law or Gustafson's law instead of Amdahl's law?
Yeah, okay. So it's a different those are if you get different kind of problems. So if I have a climate code, which I plan to run a bigger code on any on depending on how much CPU I have. So let's say I say the parallel part of the one processor climate code is zero point 0.5, right? And what's the Gustafson's law for that? All right. So, all right. So let's just pull up Gustafson's law. Right. There's no such thing.
Definitely such a thing.
All right, there's definitely such a thing. Um, what's chapter 1, right? Yeah. Oh, by the way, I meant to tell you, I'm going to have a proctor give the exam. It's going to be my graduate student Max because I want to attend a talk over in physics. Okay, so in the Gustafson's law, right, we get our parallel fraction, which is this P, which is equal to K over W plus K. So if we say that's a half, right, and we want to run on, if we want to run on 1,000 processors, then our speed up is 1 plus a half times 999. Because we get a larger amount of parallel code depending on. Uh, so if I were to try and tell you a Gustafson's law problem, I think I would do it something like first I would say, well, this is the amount of serial work in the code, and you know, this is the amount of parallel. This is the amount of serial work there is in the code, and this is the parallel fraction. Um, I want to try to figure out a way to word it so that you don't need to memorize the formula, right? Because memorizing the formula isn't so much what I'm shooting for here. What I want to stick in your memory, right, is the way the analysis works. So speed up is serial over parallel, right? So I might say the total work of a Gustafson's law problem, I might give you that, right? And then I might tell you, say, what the W and the K are, and then you would figure out the speed up, something like that. Because the idea is, right, that the K is the parallel part of the work, and you're just going to divide it by N and it's going to go away. So you're going to wind up with this. This part you should be able to easily get from this, right? If you think about Amdahl's law, right? That W is the serial portion, and the K times N is the parallel portion. If you want to make a direct map to Amdahl's law, right? You see that? You not really. Okay, so all right. Okay. Uh actually let me just make that fit in the box a little better. So the idea, right, is that we have if we is that with an Amdahl's law problem, we're going to scale up the amount of work we have to match the size of the machine. So if I am running on 10 cores, I have my sort of parallel piece of it is K. I'm going to multiply that by 10. Okay. And my serial piece is just always going to stay the same. So when I go to compute my speed up, I'm going to say W plus K times 10 over W plus K because this parallel part, K times N, is going to be run in parallel on N threads. And K times N divided by N is just K. Okay, so W is the serial portion of the work. You got, and K times N is the parallel. And the amount of parallel work I'm going to do is going to depend on the number of cores you give me, right? So when I speed something up, by running it on N cores, that means that the parallel part of the cores of the parallel part of the calculation gets divided by N, right? That's what happened with Amdahl's law. Remember? So if we go back to Amdahl's law, so in Amdahl's law, right, we had the serial portion. Hey, we had the serial portion, which is 1 minus P, and we had the parallel portion, which is P. And on the top, we have 1 minus P plus P, which is just 1. And on the bottom, we take the parallel fraction and we divide it by the number of cores. Okay, so we're going to think about this the same way, right? In a way, this is the same calculation with Gustafson's law. We have the serial portion, which is W, and the parallel portion, which is K times N. Okay, so at the top, where we had 1 in Amdahl's law, we had 1 minus P plus P. That's serial plus parallel. Here we have W as the serial and K times N is the parallel. In the denominator, right, we take that parallel part and we divide it by N. Well, the parallel part is what? Yes, and when you divide K times N by N, you get K. So that's why the bottom looks the way it does, right? You follow? And now the rest is just math. If you can do, high school algebra, you can go from here to there. Yes, McKay. Well, it's useful if I want to make a plot, right? I need to have a way to have, for a given P, I want to be able to plot what N does, right? I mean, I could still probably make a plot if I could use it that way, but it's just a question of, so in both cases with the Amdahl's law and the Gustafson's law, we wanted to scale things into something that was dimensionless. So the amount of work is probably measured in seconds. So that is the number of seconds it takes a CPU to do it if it's running sequentially, right? So W is measured in seconds and K is measured in seconds, and we need to scale that by something, right? And we can scale it by this P equals K plus K over W plus K. And and make it dimensionless, right? You could choose the P differently, right? You could put K over W or something like that. But by putting P equals K over W, K over W plus K, you get something that's guaranteed to be between 0 and 1. So it kind of does something similar. I mean, the P means something different, right? Yes, it's a normalization. All right. Does it all make sense?
When you would use, like what kinds of question you would see with them?
Well, let's see. I haven't yet formulated a Gustafson's law question, but I could say something like um, I could say that if you have a Gustafson's law, you have if you run on one processor, you get a speed of. See, I feel like this is almost a mean question. I would, if I were to try to. I think you should. I think you should worry about it in some way. I haven't decided how to ask a Gustafson's law question yet. In a way that I don't feel is terribly mean. But I guess if I said if I what?
I feel like they're all terribly mean.
Yes, well, there are different levels of mean, and I'm shooting for a 7.23 meanness, but not a 7.24 meanness, right? On a scale of 1 to 10.
Can you still go through the example that you were thinking was a mean question anyways? Just I still want to know what it was.
Well, if I said that the serial portion of a Gustafson's law code runs in 100 seconds, and the scalable portion of the code, let's call it that, the scalable portion of the code K is 50 seconds. What is the speed up for a Gustafson's law code on 10 processors? So
50 times 10.
yeah, so it would be if I would just get out my Python here. So W we said was 100, right? And K, yeah, and K we said was 50. So, and then we said 10 cores, right? So we could say our speed up now is W plus K times 10 over W plus K, right? And it's 4.
I'm forgetting it.
I think that's
Hold on, I'm right.
It is right.
wait, hold on. Just like intuitive.
Okay, so another way of doing this, right, is we want our P, right? P is equal to K over K plus W, right? And we want 1 plus P times 10 minus 1.
Man, I can't argue with the math, but I so if it's 100 total, not total, it's sequential. It's 100 sequential only.
Yeah, the W is the sequential part.
Okay, then the 50 is the parallelizable part. I assume it could be parallelizable on however many cores.
Yeah, except with Gustafson's core, with Gustafson's law, the amount of parallel work is K times N, right? So if we get more cores, we run a bigger problem.
Oh, so it's not like you're dividing K by N.
We are not dividing K by N. We are dividing K times N by N.
Okay, so the actual amount of parallelizable work is K times N. It's
What?
not K. The amount of parallelizable work is actually K times N, not K.
Yes.
Oh, okay. So we go from 500, 100 there, 5 by 10, you have 50, 150 versus 600 is still 40.
And I will always arrange the numbers on this thing so that you don't need a calculator.
For this one.
Well, you might have needed a calculator for this one. I'm not saying I would put this one on there, but I'm just. See, sometimes when you want to ask a question about something, you have to sit there and play with the way you put it on the page for a while because you want it to be tricky but not too tricky. And there's sort of an art there, right? Like I was so no surprise, you're going to have consistency questions. And I wanted to make them a little bit different, than the ones you've already done. And there was one of them in particular I was struggling for so long to make it work right and not be too complicated. But I finally figured it out. At least I think so.
Okay. I have expo markers.
Okay.
I'd really appreciate.
The problem is I'm going to try not to draw on the board because it's not so good for the recording or the person that we've got who's remote. We have a remote person. Yes, Reagan.
Plain monitors again. Just like in a very general sense.
Okay, so a monitor is nothing other than a class that contains the mutexes and condition variables that it needs to run safely in parallel.
That's too general. That includes things
No,
like
I
guard.
actually understand.
That includes things like what?
I think. I want something a bit more concrete.
No, but it is quite general.
It is quite general, but I think,
I mean, I can give you specific examples of monitors.
so let's see, that was, I think you said something like, that's a class that has all the mutexes and conditions it needs to run
Yeah, it runs safely in parallel.
safe. So you make it,
So the classic example is a parallel queue, right? We're having
essential.
what?
Sorry, I interrupt so much.
The classic example is a parallel queue, right? Where we have the NQ method and the DQ method. And this queue is a fixed size so that when there are multiple threads trying to NQ and the queue is full, right? They use the condition variable. They wait. They wait for the queue to not be full. And every so often, every time somebody takes something out of the queue, I don't know what that is. Every time somebody takes something out of the queue, right, then they signal all the threads that are potentially waiting to NQ, right? So that's an example of a monitor, which is something concrete.
No, but I didn't think it was as general as you implied, but it actually seems to be really general.
It's really general,
So
yes.
it's just, and it could be like a solution to like arbitrary problems, it seems. It's not something that's just.
Yes.
Yeah.
Example problem for overhead law.
Yeah, okay. So overhead law, that was the thing for my paper. So the idea is, and that was probably a little easier to ask about, right?
For the example problem.
All right. So if I say that I have I say I have a loop that runs in 1,000 seconds, right? And if I go to parallelize that loop on 4 cores, well, let's say I'm going to parallelize that loop onto 3 cores, okay? All right, but I have an overhead. All right, let me change my numbers. I have 1 second. The loop takes 1 second to run. Okay, and I'm going to run it on 3 cores, and my overhead for setting up and running in parallel is 1/10 of a second. Okay, so what speed up do I get for my 3 cores on that loop? So if I run it without any parallelism, right, it takes a full second, right?
In this case. So would 1/10 just be the top of the fraction?
So 1/10 would be T overhead, right? So what I could do, and actually this doesn't work out, the math doesn't work out quite as nice as I want, but so I would say T1 is equal to 1, okay? T over is equal to 0.1, right? So what I'm going to say is I'm going to say the amount of work that I have if I'm going to run this on 3 cores is going to be T3, all right? And that's going to be the amount that T1, I'm just going to divide that T1 by 3, and I'm going to add the overhead on there, right? And then my speed up is going to be what? Who can tell me? Calvin, can you tell me what the speed up is? Well, in terms of these symbols here, what do I divide by what to get the speed up? I'm going to buy, what's my initial time, my serial time? T1. And Calvin, what's my parallel time? Yep. So T1 divided by T3 is my speed up. And you would need a calculator for that when I picked bad numbers, right? I mean, I have to pick better numbers if I'm going to ask questions like that. So
Over 3 because there's 3 cores plus
the overhead, right? So, I mean, I have perfectly parallelizable loop. I'm going to run it on 3 cores, but then I'm adding overhead. Yes. Okay.
So is the overhead?
Yes. The overhead is constant. It doesn't matter how many cores there are. It's just, this is the amount of overhead there is for launching this thing in parallel. Yes. I mean, now in reality, if you're getting up to numbers like 900, you might discover that there's other factors in there. There might be an n, there might be a log n, there might be some other things that come in there to slow you down more. But most machines only go up to like 64 or whatever. So if I'd done this for an exam, I would have picked numbers that worked out that such that you didn't need a calculator. The answer would not be 2.30769, whatever. I wouldn't do that because I don't want you to use a calculator. All right.
So how does it end up working out to be T1 over T3? What happened to T over?
Oh, well, so T3 is equal to T1 over 3 plus T over, right? So T new is this, right?
Right, but
And the speed up is T old over T new. I'm sorry. Yeah, it does. Look, I added it right here, right? It's the overhead is added. You see it? T over. Yes, but the overhead is in T3 because T3 is T1 over 3 plus T over.
T over is a constant number, doesn't scale in, it's just like a number that you pick.
Yeah. So this step here, T3, right? If I'm going to match it to the slides, that is this step right here. Okay. And then this step here, T1 over T3, that's the speed up, right? That's this. You see? All right, good. Yes.
Need help understanding the most recent locks we introduced.
Okay. Could you have a specific one?
Say CLH.
CLH lock. All right. CLH lock. Here we go. So here's the CLH lock, right? It's going to have 5-4 order. So there's some tail pointer that's the basis of the lock, and it's initially pointing to this node, and the node just has a true false in it. Okay. And what's going to do, it's going to do a get and set on this thing here. So when it's acquiring, it's going to create its own Q node, right, which is going to be set to true because for locked, and it's going to swap it with what's in the tail, right? So now the tail points to this thing with true in it, and this thing the purple lock got back what was in the tail. So that means when the purple looks at it and sees false there, that means it's not locked, and purple can go ahead with its critical section. You with me?
Not quite. Let me see if I can recap this.
Okay.
There's a tail, and the tail is like a node.
Yep.
The node somehow has information about whether or not it's locked or not.
Just a Boolean, yes. Named locked.
False.
Yes.
So when it acquires it,
the way it acquires it is it creates another Q node, and it does a get and set. It swaps the one in tail for the one it created. Okay?
So that means the next person got the get and set one.
Yes.
It was like, all right, you have the tail, give it to me, I'm gonna give it to the other one. Somehow the operation is like atomic though.
Yes.
Enabled by get and set.
Yes.
Okay, what's the deal with the true and false?
That's whether it's locked or not, right? So when I'm putting something in there, I'm saying it's locked, right? So the Q node that I'm creating and putting into the CLH lock, I'm going to say that is locked, and because I want that lock first, right?
Yes.
Okay, so when I get the thing back, I'm going to get back a Q node, and it's going to be either true or false. If it's true, then I'm going to spin until it's true. If it's false, I'm just going to go ahead to my critical section.
Only one of those things existing at a time.
Yeah.
Oh, and that's why you have to create it, and it starts with one of these by default. Okay,
Yeah.
so one of them starts by default, and then every time you create one, you start with false, but by passing it around, only one.
Well, you start with true because the name of the variable is locked, right? So the true means locked. So why? So the name of the variable in the Q node is locked. So if locked is false, that means it's not locked, and I have the lock. If locked is true, then I have to spin until it's not locked. Okay? And that's basically all there really is, right? The only there's a couple of little details, but this is how it works, right? And the next lock is going to do a swap with the tail, and by doing this, we build up this implicit linked list that goes between all the threads that are waiting for the lock. All right, and the consequence of this is it's going to be a fair lock, right? Because they're all waiting in a line in this implicit queue. And the doorway is probably our get and set, right? Remember that term?
I think the part where it's acquiring.
Yeah, the part where it's acquiring the Q node, that's the doorway, right? Right. So anyway, that gives you this implicit linked list that you all wait on, and each one waits on its node until it turns to false. And then what it does is once that node turns to false, well, after it's done with the lock, right? After purple is done with the lock, it's going to set this flag to true because it's hanging on to a pointer to this other thing that it swapped in here, right? It's hanging into the one that it put in so that it can unlock for the next node in the sequence. Right?
Because it's linked there, you have to just move the information along. So
Yeah. So the unlock method, when I go to unlock, so while I'm locking, I'm looking at this green node. Right? While I'm trying to get the lock, I'm looking at the green node. When I want to unlock, I set the purple node to false. Right? So this purple node knows how to it has a reference to the green node and the purple node. And the red thread has a reference to the purple node and the red node. Right? And each one is going to wait for the color that's not itself to turn false before it can proceed. And once it wants to unlock, it's going to take the color that matches it and turn it to false.
Looking at the same figure, right? And what's going on in the figure.
Yes.
And it's like, I'm trying to, I don't know, but for some reason when it's actually like envisioning it, I guess
you're envisioning it. The vision is right before your eyes.
Funny thing. So you say that when the color is different. Is the color the previous one I had, or is it like the?
So the different color, right, is the previous one that was there. So initially there was a green one the tail had a green one, and then purple took its purple node and did a get and set, and it got back the false one, the green one. Okay, so now purple has access to two nodes. It has a memory. It has the memory address of two nodes, the purple and the green. It's going to spin on the purple, and it's going to modify the green. It's going to spin on. I'm sorry. It's going to spin on the green and modify the purple to unlock. Reagan. You could take a crack at explaining it.
So yeah. And purple is over here, and it picks the thing up out of the green basket, and it takes it and puts it in the purple basket, and then it's whoever's next in line's turn. Once the thing makes it to the side to this side. Does that make?
Takes it from the green basket. Purple basket.
So I guess what you're thinking of, the thing that you're
It's like right?
the false. The false value, value is moved from one basket to the next in order to pass the lock along. Does that make sense?
That makes sense.
A balloon or something. Take it from over here, you carry it, you put it over here, and the next person takes it out of this bucket, bring it to the next bucket, and it keeps going.
Right, so we're describing something about the transfer
Yeah.
process here.
When the false balloon ends up in that bucket, then the next person can take it.
Okay. And that's what this, yeah, that's what, okay.
Okay, and then the other part of this, right, is that the purple will save this green Q node to use as its Q node next time it wants the lock. So the Q nodes get recycled. Okay, and the recycling of the Q nodes is the difficulty for NUMA systems, right? So as I was starting to say before, we have Queen Bee4 on campus. The Queen Bee4 CPU has 4 NUMA domains inside it. So that each group of 16 cores is in a single NUMA domain. So we have 64 CPUs, 2 sockets, and 4 NUMA domains. That's what they say. So each socket has a chip that has 2 NUMA domains. I don't know. I'm not a hardware designer. But that's what they do, right? It's just a question of, I think it has to do with, trade-offs and getting the wire, how many wires are going into the memory and how much bandwidth you can get and so forth. Yes, Reagan. Okay.
But doorway and waiting interval.
Yes.
What makes it a doorway interval? Like I get the waiting interval because it's a while loop to waiting.
So the doorway is getting your place in line, right? So that was for the bakery lock. And the concept of the doorway and the waiting is the doorway is the part where you can't control the order, right? That's where you're getting your place in line. You're establishing your ticket number.
Get the place in line as part of the doorway.
Yes. And then once you have your place in line, then you're waiting, and it becomes fair.
On quiz 2, the question about the Peterson lock, can you run through that and explain?
Yeah.
Both threads
Right.
get to the critical section.
Yeah. Okay, so let's just do it sequentially, right? Thread 0 comes in here, sets me to 0. Other is 1. Flag 1 or flag 0, I set to 1. Victim, I set to 1, right? That's the other one. Okay. Okay, so I set flag 0 to 1. You got that? Now I'm setting the victim to 1. Now I go to the while loop. While flags.other is not 0. Well, flags.other isn't raised yet, right? The other thread hasn't run yet, right? So I automatically make it through this past this while loop, and I have the lock, right? Okay, so now I'm happily chugging along on my lock. Thread 1 comes in. It sets me equal to 1, other equal to 0, and it sets flags 1 to 1, right?
Mm-hmm.
Then it says sets victim to 0, right? Now we go to the while loop. While flags dot get other, that is, while flags dot get 0, is the flag raised? Yes. So that part is true. And victim equals me. Is the victim equal to me? No. I set it to the other. So I make it through this loop and I go into the critical section. So just if they just execute sequentially, they both get in.
And the correct solution.
You see, if you set victim to me, then it's fine. Based on these questions, I have to come to the conclusion that consensus is the easiest topic for all of y'all.
Going in order.
Yeah. Yes, Ryan.
We spoke about the read, modify, write instructions. We also spoke that hardware these days doesn't do that. Is that right? They do.
They have read, modify, write instructions, but they have, instead of compare and set, they have load exclusive, store exclusive.
But does knowing that give us any insights as to why we don't do that? Or
I don't know why they do that. In principle, the two things are equivalent. I have a theory that the load exclusive, store exclusive programming paradigm makes it harder to fall victim to the ABA problem, which we haven't discussed yet. Reagan.
Quiz 4. The big chunk of questions.
Uh,
The execution questions. The ones that are like the instructions consensus number. Oh, Joe, we're still getting there.
all right.
Going in order.
Okay. Consensus numbers. Yep. Yep, I see them.
So atomic right makes it 2. Why?
Well, we did that in class. Remember, we wrote to 2 of 3 memory locations atomically, and we had what we did is we took we had one processor write. We had processor 0 write to 0 and 1, and processor 1 wrote to 1 and 2, right? And each of those memory locations had 3 possible values: unset, 0, and 1. Yeah, it's that thing. Yeah.
The thing you 3 bucks.
The thingy with the 3 boxes, exactly.
It has to be atomic just to make sure that the writes occurs, just it doesn't matter what order, because we have our system.
Well, if the writes happen atomically, they happen at the same time. That is the order. At the same time. It's impossible to observe a time when one of those 2 places is set and the other is not. That's the idea of atomic.
So on a single patch, is it, so if we have 3 patches, is it the entire whole? Is this atomic?
I don't know what you're saying. Let me pull up the
Oh, sorry.
picture.
Consensus 2 with 3 memory locations.
Yeah.
Are we considering the entire, all 3 as a single thing that needs to be atomic, or is it just?
We write to 2 of them out of 3. We don't write to all 3. We write to 2 of them out of 3. That's the trick.
Yes. Talking about the status, like what makes it atomic.
We just hypothesize that, there's a magical instruction that says write to 2 memory locations. Well, the way we did it, right? We have a double assignment interface. So we have this thing that looks like this, right? It's got assign I1, I2, V1, V2, right? And the question is, can you make that with regular memory? And we go on to prove that you can solve consensus 2 with that. So therefore, you can't make that with regular memory. In fact, such a thing probably doesn't exist anywhere. Yes. What?
Modify rights have 2 consensus unless it was non-mutable.
Okay, so the way I would prefer to say it is Regular memory has consensus 1, which means you can't solve consensus at all with it. The get and set operation has 2, right? And any commuting operation has 2.
But what about non?
That's going to probably, you have to think about it a little bit, but it's probably going to be 3 or more. Anything that doesn't commute is probably going to make 3 possible. Yes, McKay. Percent. We did that one in class. The modulus operator. So imagine that I have a read modify write modulus operator. Suppose I have a memory location that's initially 5, right? If I do first I do a modulus of 6 on that, or no. Let me rephrase it. Let me say I'm going to start with 8, right? Initialize my value with 8. And I'm going to do a modulus of 7 with that. What am I going to get? 1. And then if I go with a 6 and a 5, and I apply it to that 1, what am I going to get? Right. Okay, so suppose that instead of that 7, I now use a 6. What is 8 modulus 6? 2. And now if I subsequently go in with a 5 and a 4 or something like that, it's still going to be 2, right? And then if I go in with a 5, right, then it's going to be 3. And so what's going to happen is I'm going to be able to distinguish which of them moved first, depending on whether I wind up with a remainder of 1, 2, or 3. That'll be the one that moved first. So the modulus operator, it's fairly easy to build a consensus 3 object, and probably any number consensus I want, right? Instead of picking a small number like 7, I could pick, 1 million. And then my first thread can go with 999,000, 999. And then the next one can go in with 999,998. And they're all gonna get their number, right? And I'm going to be able to easily solve probably consensus a million that way. Make sense? So it's generally, the point is, if it doesn't commute, see the problem with the commuting operations, if I add 1 and I add 2, right, at the end, that's just adding 3. I can't tell what order it happened because it commutes. I can't tell the order. But if it doesn't commute, that probably means I can tell the order, right?
Probably.
You have to think about it. You have to look at the problem and say, how would I build a consensus 3 out of that? And you probably will think of something. Yes, Reagan.
Yeah.
Because it needs to have a memory location for each of the bits. And even worse, if you want to prevent the false sharing of the cache, you have to pad it with like a full integer or several integers, right? So it's a memory hog. It's probably the worst memory hog of all the locks. The Peterson lock? Oh, the 2 counter lock. Oh, well, the way it works, right, is it's based on the metaphor of a bakery, right? The first thing is a ticket. You get your ticket, and that's your place in line. And then you have the other thing that's the serving, right? And it just counts up toward it. So the process of getting your ticket gets you your place in line. That's your doorway. I feel like a moment of silence needs to follow that. Reagan's questions are finished. No, you. But what I'm saying is you're the one with all the questions. Like in the last class, you came here. All right, I have questions, and we just marched through them. So you're out of questions. Is everybody out of questions? Who has No, Tristan.
Yes.
Yeah. Hmm. Okay, so we have a Q node. Well, let's go here. So the goal here is to spin on local memory. We don't want to recycle nodes the way we did with the CLH lock. And so we start out with kind of the same setup. We've got a tail. And this time our Q node is going to have, in addition to a Boolean, it's going to have a next pointer on it. So our Q is our linked list is going to be a little more explicit. And what I'm going to do is the same step. I'm going to swap. I'm going to put my Q node into the place of whatever was there. Now, one of the differences with the MCS lock is we allow, so CLH lock always has some kind of Q node sitting in the tail, right? Whereas the MCS lock will have a null there when the lock is not in use. And so we're going to acquire this thing, and we're going to acquire this thing by swapping as before. Now, if we get the null back, then we know we got it. But otherwise, what we're going to do is we're going to have that Q back. And the second one is going to do the same thing. It's going to swap. It's going to get the purple one and it's going to put the red one in just as before, right? So this part, it's all the same. And the red one is going to spin on its own object instead of on the other color, right? So in the CLH, we spun on the other color, but in the MCS, we're going to spin on our own. So, and then when we release the lock, what we're going to have to do is we're going to look into this purple linked list here, and we're going to follow the next pointer to find the red one, and then we're going to unlock it that way. Okay, so with the CLH, the get and set, we got two nodes as a result of that. We had the one that we started with and the one we got out, and those are the two in our that were the elements of our linked list. But with the MCS lock, we have one, right? We have the one we put in, and what we get back, if it's a null, we have it. But if we want to unlock, we have to actually follow the next pointer on our own object over to the next thing, right? And so we're counting on that thing, that red one, to fill in the next pointer for us.
So it acquires a lock, it's null or it's good, but like it'll create a new node regardless. So it'll create a new node into memory.
Yeah, it's just going to have one that it reuses, but yeah.
Okay, so we can just reuse the same node. And so it'll if there is something in there before, it'll point that the node before to its node.
Yeah, if there's something in there, if it comes back non-null, that's one of it's either the holder of the lock or some other thread waiting on the lock, right? And we have to take that Q node and fill in its next pointer if we get something non-null, and then we can spin on our own memory once we've done that.
So if there is something, we'll say that this lock is true. That's what we initialize memory. If it's not. If it's false, if it's null, we'll initialize our own memory false. We can go through.
Yeah, we can go to the code. So here's how the lock method goes. We get it. It's allocating a Q node, but we can reuse it. We're going to do a get and set. Get and set swaps. Yes. Okay, and then what we're going to look at our predecessor. If our predecessor is not null, then we're going to set our Q node flag to locked. We're going to set it to true. And then we're going to set the next pointer on the predecessor to point to us, right?
Based on hey.
Right.
System get set Q node. What does that return a pointer to? Its tail.
Yeah, whatever's being held in tail. Ta- I mean, atomic tail is an atomic reference.
Sorry, I guess the previous one is there and then it says it's count.
So that's and it says the current one that's after the objective.
So the is it making sense to you?
Stare at it just a little bit. You point at this one and then this one. But we got null and it skips all of that. He doesn't do any assignment. The next one. Okay, so I guess in unlock we have to pass it over or something. And then
So in unlock, what we have to do is we look at our qnode.next field and find out if it's null. If it is null, that means, that nobody has set it yet. So that might mean that nobody is waiting for the lock yet, but it might not mean that, right? So what happens is there's a space when I'm getting the thing, right? I do between when I call get and set and when I set pred.next, right? There's some amount of time goes by. So if I go and I look at when I go to do the unlock, when I say qnode.next is null, I don't know whether there's nobody waiting or they just haven't gotten around to setting the next field yet. But what I'm going to do is I'm going to hope that there's nobody waiting. And so what I'm going to do is I'm going to cast the tail with the Q node to null, right? So if I was the last person to do a get and set on the tail, then the tail will contain Q node, and this compare and set will succeed. Okay. If it succeeds, then the tail is set back to null, and I'm done unlocking. Yeah.
sink in and then it actually just like.
So here's the thing, right? When I want to get the lock, I do a get and set on the tail. And then if I get something back, if I get a predecessor back, then I have to set the next field on it. Now, if I'm in between, now when I go to unlock this thing, I have to take into account, right? At first I look at my next field. And if the next field is null, then I know that nobody has assigned that next field yet. But somebody may have done a get and set on the tail. So what I'm going to do, in an attempt to unlock this lock, I'm going to try to set the tail back to null. But I'm only going to set the tail back to null if my Q node is the one that's in the tail.
You're gonna set the tail to null if my Q node is the one that is tail.
Right. So the point is, if somebody did a get and set on the tail, then my Q node will no longer be there. Their Q node will be there, right? And so if somebody else has done a get and set on the tail, then this instruction will fail, right? The cast of Q node to null will fail. But if nobody has done a get and set, then this will succeed.
If somebody created a new node and said that that's the embed list before they set the next pointer on this one, and that means that there's somebody acquiring the lock, but they haven't linked the node to the next. The next.
Sorry.
Okay, let's back up, Barrett. Let's back up again. All right, so we're locking, right? So the first step in locking is we do a get and set. Right? We take our Q node and put it into the tail and take whatever's in the tail and take it out. And that becomes our predecessor node. Right? If the predecessor node is null, that means the lock was free and we can just go about our business. Right?
Sorry, I'm getting kind of confused about the model for some reason.
Okay, so look.
Well, I guess I have to just like I really have to like visualize it.
Let's go back to the pictures then. Let's go to the pictures again, right?
Let's see.
So we're initially like this. We create our purple Q node, we allocate it. Okay, we're going to swap with the tail. Okay, so now the tail is pointing to our purple node, and the thing that we've got back, our predecessor, is null, right? It's this 3 lines here, that's null, okay? You with me?
I understand what you're saying the step there is, but I just don't get the pattern.
Well,
I
just,
don't-
okay, so, but you got the step.
We put tail pointed into the purple thing, and then the purple thread points it all.
Right, so the purple knows, if it gets a null back, it knows that it has the lock. Now, while it has the lock and it's doing its thing, red comes along. Red does the same procedure. Red creates a red Q node, and it does a get and set and swaps it out. It gets the purple node back. Okay, it did not get null. Because it did not get null, it has to potentially wait in line. So what it's going to do is it's going to set the next field. It's going to set the next field on the purple node to point to itself. It's going to set its locked flag to true and set the purple nodes and fill in the purple node's next pointer to point to itself. So it's telling, hey, purple, when you're done with the lock, please give it to me. That's what filling in that next field does. Okay? And then it just spins on its own value, waiting for that true to turn to a false. Now, the thing that we're trying to discuss is purple's unlock. So what can happen is purple is trying to unlock this thing. And it can be that we're at this stage, right? So red has done its swap with the tail, but it hasn't yet filled in the next pointer. Right?
Because it was in the lines of code, like you do one before the other.
You have to do one before the other. You do the get and set before you fill in the next pointer. You can't fill in the next pointer until you get the predecessor, right? If you don't have the predecessor, you can't fill in the next field for it. So, okay, but so what's going to happen is there's 2 possibilities. Here's one possibility, all right? I'm unlocking and this is the situation. Now, what I'm going to do to unlock in this situation, if I get the predecessor back and it's null, which it is, I'm going to attempt to cast the tail pointer from my purple node to null. Right? If that compare and set succeeds, that means this is what the universe looks like. It's just me, my purple node, and the tail. Right? But on the other hand, if this red one has done this step, if it's done the compare and set, right? And I look at this and I say, well, this is set to null. I don't have anybody that out there there's probably nobody out there waiting for a lock. So I'm probably good to go. So what I'm going to do is I'm going to compare and set with purple against the tail to null. And that will fail because the tail is now pointing to the red, right? Red has done the first step of the lock. It's done the get and set. And that prevents the cast from succeeding. Right? This is no longer purple. So compare and set from purple to null is not going to work. It's now red. Got it?
Honestly, I got lost like 10 seconds.
It's okay. So look.
I'll have to study it more for sure.
All right. So, but look, if it's here, all right, if I do a cast, it's going to succeed here, right? If I do a cast from purple to null, it's going to succeed because tail is pointing to purple. Get and set, yeah. Right? So tail did its get and so purple. So the first step in getting the lock was purple created its node and it did a swap. It did a get and set. And now the tail is pointing to this purple node. And the thing that came back from the get and set was null. That means I have the lock. Okay. Now if I go to unlock at this point, right, I see that my next pointer on my Q node is null. And so what I'm going to do is I'm going to attempt to set the tail to null. But I'm not just going to blindly set it to null. What I'm going to do is I'm going to try to compare and set from purple to null. And if this is what the world looks like, it's just me alone with the lock, that's going to succeed. right? Because this is still pointing to the purple node. So compare and set from purple to null is going to work, right?
Sorry, this is just opaque right now.
Okay.
I'm really gonna have to study this later.
Okay. All right.
Okay, you can move on.
All right. Who has a question?
You explained.
McKay raised his hand first. I can't hear you.
I have a small about this
Yes. Okay.
in the example.
Yeah. Thank you for the slide number.
It does that. My question is, wouldn't that would leave a possibility of it unlocking without block? Right? Because if it's going to finally unlock, or if the method to exit before you got with the try block, would that mean that you have a possibility of unlocking without ever locking a simple lock? Like there was just some catastrophic error.
So the idea behind the finally, right, is I think it could be to guard against some kind of error, like condition.await throws an exception, right? It could be to guard against that. And yes, it would probably be left in a bad state if that happened. Well, let's think about this. So one of the real purposes of the finally is if owner equals me hold count plus plus and I return. That makes sure I unlock when I return. And it's just sort of like, just making sure that I didn't forget to unlock when I returned. Right. So that's what that does here. It's not so much guarding against an exception, it's guarding against, just forgetting to say unlock, right? Well, it is. I mean, it gets its own ID. I think that's harmless enough. But here, when it's saying while hold count is 0, condition await, I think it hasn't incremented hold count or done anything. So I think even if it dies at this point with an exception, it's okay, right? And that's the only place where it could die with an exception is right there. Because everything else is just assignment, and that's not going to cause an exception.
And I don't think that there's any.
Yeah, I can't think of a way an exception would occur anywhere but condition await. Well, I mean, you could do something stupid like if here's a way you could make it happen, but it's really stupid. Is if instead of an int up here, if I had int where it has the hold count, if I had the hold count declared it as capital integer instead of int, and then I had capital integer be null, then assigning to it, then incrementing it would be a null pointer exception. But that would also be harmless. So even if I did something stupid like that, when I tried to do a hold count, I'd fail.
Even though realistically no exception could occur, there weren't exceptions to occur, and you were to finally unlock before you got to that lock state. Is that a usage error because you're unlocking before you lock?
Well, okay, so the very first thing in the try block is a lock, so we can't unlock before we locked. But unlocking before you lock would be a usage error. But once you get into the try block, yeah, if you had some other code before you did the lock, and that code exited or threw an exception, then you would lock without unlocking, and that would be an error.
I feel like
I think it's okay to say it's just the very first statement in the try block. I think that's just as good. Actually, it's better, right? Because if I put, I mean, in a way, it's better, in a way. So if I put the lock before the try block and something happened that I didn't get to the try block, then I would be in a bad state. I'd be locked without unlock. But if it's either the first thing before or the first thing after the try. Either one of those is just as good as a principle, I think. If you put something between that try and that lock method, that's where you have problems.
That were the case you're saying, you should have the lock either before.
Or immediately after the try. Because if I do a lock and then something happens to me before I get to the try, then I never unlock. If I don't get to the try, the finally only happens if I get to the try.
I was making the assumption that finally always.
No, you have to get to the try. All right. Yeah, that's just how Java works. Next question.
Your person asked any?
No. There's a person on Zoom, and I see no questions down there, so. Ah, there it is. I could swear I looked there a dozen times. Here's my MCS lock. Ta-da. My beautiful MCS lock. Okay. What do you got? Okay. Okay. Well, I don't know how much detail Lucas went into. So we have a broadcast and reduce and a barrier, right? So we're going to send a value out to everybody from the center, or reduction operations are going to be things like addition, right? They're going to be commuting operations, commuting binary operations. Yes. I haven't finished making the exam, but I do try to hit all the topics in some way. Well, since this is one chapter out of like 5 or so, there should be, 1 or 2, something like that, something proportional. And then there's the barrier, right? We discussed what a barrier was. That's when they all wait up at one point. So everybody stops at the Buc-ee's.
Will the content on the test be mostly like the textbook slides?
I mean, yeah, anything that we've discussed in class is fair game. I'm not going to ask you questions about things we've never discussed in class. Didn't you notice there was a footnote in the book? Half your grade is based on that. Reagan. I mean,
General whole thing, is there any particular topic?
well, I don't know. There's one that stands out. I mean, consensus, it's you want to have that in your head pretty solidly. You want to have the basics about the locks in your head, you know. You want to know how the Peterson lock works if you get a mutation of that. You want to know the progress conditions, right? You want to know terminology that we've used like monitor and lost wake up. You want to know stuff that was on previous quizzes. Anything that's on that previous quiz might show up either again or in a mutated form.
Is there anything you think that as a class we all did really bad on?
Nothing stands out like that, at least not with this class. Um, let's see. Let's look at these at the so safety versus liveness. Remember that? And how did we, what was one of our keys to solving, say, dining philosophers with getting the locks there? What is it you do for, what do you do for lock safety? Yeah, that's right. You want to give them a canonical order. Um, that's one of the things you want to do. What's another thing that you want to do for lock safety?
Use try and find.
Use try and finally. Yeah. Um, you also want to make your critical sections as small as possible. I mean, you want to know there's composability, right? Remember composability? So when we talked about it's come up in two places. Can anyone remember what those two places are?
Thing happened.
So what in particular are which chapter are you thinking of? Okay, so chapter 8, we were talking about locks. We say locks are programming with locks is non-composable. And we had an example for that. The point was you can't just look at a piece of code and know whether it's safe or not, safe from deadlock or not. Because you don't know really at any point when you're calling something that's going to get another lock on you. So we said locks were non-composable. And there was another place where composability came up.
Was it in the consensus chapter?
It was not the consensus chapter. But he remembers.
Good trying,
I believe that you're really trying.
that's one thing. The homework was done.
So let's see, what chapter could it be? All right. So the thing that we talked about that is non-composable is sequential consistency. You remember that? 3, yes. Sequential consistency. We had if you apply sequential consistency to each object, you can't necessarily apply it to all the objects. And we had that like closed time like curve picture, right? Where the different objects were arranged such that it all went in a time loop. All right. That was 3. All right, so this is the part where I wish you good luck on the exam.
See how that's.
Oh, you know, even if I don't, there's a curve.
You only have to do better than 3 other people and stuff.
Yes.